Welcome, everyone. My name is Prem Chandrasekaran. I'm one of the regular co-hosts of the Thoughtworks Technology Podcast. Today, we're joined by Neal Ford and Mark Richards, and they're going to be talking to us about the intersection of architecture and a variety of aspects of the software development lifecycle. We're going to do this in two parts. In today's episode, we're going to talk about what these intersections are, and in an upcoming episode, talk about how these correlate with code and implementation. With that, let's get started. Hello, Neal, and hello, Mark. Would you quickly introduce yourselves?
Sure, I'll go first since you probably have heard my voice a lot. I'm sometimes a guest and sometimes host of this podcast. I'm sitting in the luxurious guest chair today to talk about this, since this is some IP I'm creating with my consistent teaching and writing partner, Mark Richards, who's also joining us today. Hi, Mark.
Hi, and thank you actually for having me on yet another Thoughtworks podcast. I think this is my third one, if I'm not mistaken, maybe even fourth. So it's great to be back on the podcast.
We're nothing if not consistent.
Excellent. It's great to have you both. And let's kick off today. So what is this thing that we're calling the intersection between architecture and implementation? Sounds very intriguing.
We have a term that I did a little poking around and discovered, which I love, but is way too obscure to talk about without providing some context, which is the term nexus. So it's the term nexus, but it has the little hat over the U and is pronounced nexus. And the definition is it's plural nexus. So it's a combination of nexuses, which is also legal plural. But it's really this idea that there's not one intersection of architecture and implementation. It's the intersection between architecture and implementation and data and infrastructure and engineering practices. And in fact, 9 different places that we've concretely identified where architecture intersects with other parts of the organization. I've long said that architecture is sort of unique in that we have a unique perspective on our ecosystem because we understand technical capabilities, we understand business constraints, we understand what infrastructure capabilities are available. Maybe we understand where the enterprise strategic direction is going. And so that's taking advantage of this sort of unique vantage point that we have inside organizations.
Well, and it kind of carries on from actually both of our books, Neal. Well, I should say all three. The Fundamentals of Software Architecture, our Architecture, the Hard Parts, and our recent Head First Software Architecture, where we developed a lot of qualitative analysis in terms of comparing various architectural characteristics between different architecture styles to know really which architecture would be most appropriate for given situations. Yet the problem is we do that and architecture still doesn't work. And this is really that next step of realizing that architecture rarely lives alone. And as a matter of fact, there's a lot of external forces that influence a software architecture and vice versa. There's a lot of architecture can influence a lot of external forces. We call these external forces intersections of architecture. And our real goal of all this material, including this podcast, is really to align architecture with these different facets of the environment.
Yep, and eventually be able to express it a lot more directly than we are doing now. But we want to, so this is really a 2-part podcast. The first part here is really describing these intersections and what we're talking about here, because it's, I know, impossibly vague and abstract right now. We're going to try to make that more concrete. And then the next time, the next installment of when we talk about this, we'll talk more concretely about how we're actually documenting all of these intersections. So let's start with a good example of the first one that Prem mentioned, which is, and probably the most obvious one, which is the intersection between architecture and implementation. Mark, what do we mean when we talk about that intersection?
Well, I've got a question for you first. And that is, Prem, I bet you can answer this. What are the famous words that every architect says when asked a question? Should I use A or should I use B?
Well, I know that that's a very standard consulting answer. It depends.
Exactly. It depends. Well, it turns out that there's another common phrase that most, if not all, architects use. And when asked a question about A or B, the other response is, well, that's an implementation detail. And this is really the crux of that intersection between architecture and implementation. Because if we don't pay attention to how that architecture is implemented, quite frankly, it rarely works. And when we talk about this intersection of architecture and implementation, there really are three areas within this intersection that architecture has to be aligned with. And the first is an operational alignment. The next is kind of a constraints alignment. And then the third is a structural alignment. And the way we write source code, the way we implement our architectures, we have to adhere, for example, to certain constraints. Maybe in a traditional layered architecture, the presentation layer is not allowed to access the database directly. It has to go through all the layers. That happens to be a constraint. Maybe we have a particular constraint within microservices where we have a group of services that cannot and will not communicate with other services. They have to remain standalone. These are kind of constraints that we have within an architecture. And if we choose to implement those constraints differently, it's an example where the architecture becomes misaligned with the architecture. A classic example is where an architect chooses, for example, microservices to have really great elasticity, really great scalability, and also a nice change control. And with that scalability, let's say to 500,000 users, microservices is actually a good choice. And architecturally, it will scale to 500,000 users. But the developers then notice that services need to communicate with each other. And this coupling is going to slow things down quite a bit. So the developers choose, let's say, to use in-memory replicated caching, so that if I need data from you, for example, Prem, instead of having to ask you for it, we're just going to use a shared in-memory cache where each of us have that in-memory cache. This way, I have your data, and I no longer have to talk to you. This is decoupled. It's much faster. And this is actually a really smart move. However, both of these decisions are good. But based on the scalability of 500,000 users, once we go into production, you can suppose what happens after about 40,000 users. Because of that in-memory data grid, which is in memory, we run out of memory in our virtual machine, in our pod, whatever that container is, very quickly. And this is an example of operational alignment where the architect focused on scalability, but the developers ended up focusing on performance and decoupling. And this is a prime example where an architect has to be involved in the implementation of that architecture to ensure alignment.
To overuse a metaphor a little bit about building architects and software architects, there are serious constraints on when people are building a building about just randomly removing a wall, like a load-bearing wall. We need the same kind of constraints as software architects, because as people are implementing our code, it could be, well, these two components don't talk to one another in this diagram, but look, I can just draw a line between them. Now they're talking to one another, or implicitly do that by doing it in an automatic import. And suddenly now things have dependencies that they shouldn't have. And so this is a way of expressing some of those load-bearing walls that are critical for the structural support for the application.
So what you seem to be, what you both seem to be saying is that it's definitely possible for architects to design something that is architecturally sound and also implementable by the team.
Correct. Yes. And the fact that the goals of the architecture and those constraints and those decisions are actually adhered to, and the structure of the code matches the structure of that architecture. So, yeah, this is perhaps the most common misalignment that at least I see, and I think Neal sees as well, in terms of having architecture actually work.
But the nice thing about this is there's lots of really nice tooling around traditional architecture fitness functions with tools like ArcUnit or NetArcTest or PyArcTest or TSArc. These are all tools that allow you to create that kind of governance alignment. And that's the kind of stuff we talked about in the Evolutionary Architecture book. But this is where the current IP that I'm working on goes way beyond evolutionary architecture, because we focus mostly on things like implementation, but now we're going much deeper into all these other intersections, including a really critical one that people don't nominally think of as having a serious intersection with architecture, which is data.
Mm-hmm. Oh, yes. Another very common overlooked intersection where, unfortunately, and this has just been my experience, that still, even today, too often, architects treat data, and, well, developers, we all treat data as kind of an orphan, something that really doesn't matter too much. And in fact, choosing the wrong topology for your architecture can have devastating impacts. And when I say topology, what I mean is the three basic kinds of topologies we have, which are monolithic databases. We can have domain-based databases where we break up the data by specific domains. And then all the way to the other end of the spectrum, which is kind of the dedicated data, or what's known as the database per service kind of topology, where it's typical in microservices, where each service has its own data, and that's what forms that physical bounded context. It's interesting, out of all the 8 common architecture styles, it does in fact matter which topology you use for the success of that architecture. And most of us are familiar with the monolithic topology constraints in terms of scalability, change control. These are two things, fault tolerance, that can plague an architecture. And if we're choosing an architecture style for those reasons, and we're using a monolithic database, we likely won't achieve those kind of capabilities. As a matter of fact, if we even look at something like event-driven architecture, kind of raises the question, we talk about events and triggering events, responding to events, but where's the database in event-driven architecture? And, if we use a monolithic database topology, we might not achieve the high levels of scalability and responsiveness and elasticity that we enjoy from event-driven architectures. But by the same token, if we use the other extreme, a database per service, where every service in our event-driven architecture has its own database, we've got great elasticity, great scalability, great fault tolerance, except when I need your data. Because now I don't have access to that data anymore, and I have to start asking you for it, which all of a sudden synchronously couples our lovely asynchronous architecture. So you can see there's quite a range.
You should describe the two anti-patterns that we've identified, or you identified, in terms of granularity and messages.
Oh boy, you mean from event-driven architecture? The swarm of gnats is one you're referring to, right? Yes. Yes, the swarm of gnats event anti-pattern. This is a anti-pattern Neal and I coined, where a gnat is a small flying insect that both Neal and I know very well from our locations. where you're going out for a walk or you're outside, and these small, almost invisible little flying insects, just hundreds of them, swarm right in front of your face. And consequently, this kind of anti-pattern comes from the granularity of derived events within event-driven architecture. And the fact of triggering too many fine-grained events is where this anti-pattern comes from. I still like this name, Neal.
It's a great name because a lot of people have experienced gnats. One other important aspect of the architecture and data intersection has to do not just with topology, but the kind of behavior. So we have all grown up to understand that the relational database is magical and it does magical things for us. And we hate to give up on magical things like referential integrity checks and cascading deletes and foreign key checks for us and atomic transactions and all those wonderful things. And we sometimes have to give those up when we move to a topology like Mark was talking about in a distributed architecture. And one of the common arguments you have as an architect is when you go to data engineers and try to describe this whole idea of breaking data up into tiny, tiny pieces, that's just not the way they're wired. That's not, since they were little bitty data engineers, they were taught that, it needs to be monolithic and joined together. And that the only way you can do some of those things is within the database, like referential integrity, for example. But you can actually do this from an architectural standpoint. Just like we talk about eventual consistency when we talk about transactionality, we can also talk about eventual referential integrity and eventual cascading deletes and eventual foreign key checks by building into the architecture things like durable message queues that say, when you delete this from this service, post a message to a durable message queue that guarantees that cascades to all the other services that should no longer have a reference to that. Now you're fixing that foreign key constraint across your architecture, but you've changed. So fundamentally, a foreign key constraint is governance. We rely on the relational database to do that, but we can also implement it ourselves if we have to go to distributed data for the reasons Mark was talking about, for scale or elasticity or availability or fault tolerance or something like that.
Well, and also it has to do within the intersection of data, again, not only with the topology, but as Neal was saying, the type of database that we also use. And there is an alignment that happens here as well, where in fact, relational databases are a great example where the ease of learning and data modeling rates pretty high on a relational database, as does overall consistency and transactionality. However, if scalability, elasticity, throughput, and fault tolerance and partitioning are your main primary concerns, then relational databases present an alignment risk. And the type of database is actually kind of interesting because what really drives the type of database that we should use is the nature of our data. If data by nature is relational, a relational database works well. If we're storing a bunch of key value pairs, a KV database like DynamoDB works really well. And the same thing with associations with graph data. That's when we would use things like Neo4j or any of these other kinds of databases. And what are the other misalignments that can occur is what these databases are good at and what they're not good at. When we talk about scalability, throughput, availability, ease of learning, the cost associated with these.
Yeah, so I have lots of questions on this because this is one of my pet topics, right? So here is a question for you folks. How do you see architecture playing a role when having to manage the balance between, let's say, a real-time or a batch processing data architecture? Is that a relevant question in this context?
Well, it is because there are a whole bunch of different trade-offs that you have to think about there. So the first thing you'd have to do is delineate what trade-offs you're talking about there and what impacts that have. So, for example, batch processing is a steady stream, but then what happens if something happens during the batch processing and you get a failure? How quickly can you recover? How quickly do you have to recover? Versus in a message-based system, what happens if you lose messages? One of the common patterns in systems like that is to say, okay, if we're handling a stream of messages, don't do error handling as part of the stream. As soon as you get an error, kick it off to an error handler and keep processing messages, which is not an option in the batch world. So that absolutely has an impact on architecture, but also things like infrastructure, which is actually our next intersection, because now with modern capabilities like infrastructure as code, you can legitimately set up a self-healing system that says, oh, we got messages coming in and my queue is starting to fill up. I'm going to spin up an alternate queue and start deferring messages to that and spin up more infrastructure. Of course, there's obviously a limit to this when you fill up Amazon cloud and, and the bill comes. But we have some unique capabilities here around handling some of those things in a graceful way.
How does cloud-native architecture redefine the relationship between architecture and infrastructure? Maybe you answered some of that, but that was something that I was going to ask. But
well, this was actually going to be the exemplar example of these intersections. But since you asked it now, this is a perfect time to talk about it because we're talking about data and infrastructure, which are the things that are impacted here. So this is a great example, and I wished I could take credit for this example, but I can't. On a previous episode of our podcast, it was February, I think it was 22, we had Dave Farley on the Thoughtworks Technology Podcast. Mike Mason and I interviewed Dave Farley, and Dave Farley is famous for being one of the architects of LMAX, which famously coined the term for mechanical sympathy, because they designed this really incredible architecture that took advantage of the size of the CPU's cache and a bunch of crazy stuff like that managed to achieve 6 million transactions per second famously. But then Mike very wisely asked Dave the question, well, with cloud, does mechanical sympathy even matter anymore? Does anybody care about that? And Dave said something, it's a great insight, and it's a great illustration of this intersection concept that we're talking about. Why do we normalize data? Besides the fact that Peter Code told us to, and I guess we're supposed to do all the stuff that Peter Code told us to do, but why do we normalize data? Well, since time began, CPU is cheap and storage is expensive. So one of the reasons that we normalize data is we carve it up so we can store it as efficiently as possible, then piece it back together as we need it. Makes perfect sense. And we've cooked that into our brain so much that, of course, you normalize data. But when you move to the cloud, it's the manipulating and moving it around that's expensive. Data at rest is essentially free. And so instead of normalizing your data in the cloud, you should duplicate it and shard it everywhere. Now, talk about a mind shift. Good luck, architects, going to your data engineers and telling them, hey, all that normalization you're doing? Forget it. We're not doing that anymore. We're going to stop normalizing our data, and see what kind of interesting conversations that generates within your data engineers and your organization.
Let me play devil's advocate for a second, right? Absolutely. So I totally understand with the cloud, the semantics now change. You probably don't have to normalize as much as you probably did when we were in a lot more constrained environment. But then it still comes with some sort of overhead, right? Now I've got 15 different copies of my data, and who knows where. And then now when something changes, you have to go update it in 15 different places.
That's right. Well, but so I'm sorry, we never promised you that we were going to have perfect solutions. It's about trade-offs in software architecture. But again, if you have that behavior in the cloud, you can do eventually referential integrity and consistency and say, I've got this in 5 different places. I have fitness functions that say when this disappears here, make sure that it also disappears from those other places. So that's a good example of translating something that nominally happens in a database, but we need, because of architecture concerns, to move it to a cloud environment, replicating the same governance behavior, but in a different way. through architecture.
Well, and it's interesting too, because this whole discussion about these trade-offs always seem to boil down to CAP theorem. And CAP theorem basically says you can have network partitioning, which is the P, or consistency, C, availability or network partitioning. But it's an interesting case that in distributed architectures, which most, not all, but most cloud-based architectures are necessarily, or I shouldn't say necessarily, but typically distributed, that only leaves us architects with two choices: consistency or availability. And it's not surprising if you look at our star ratings in the Architecture of the Hard Parts book for all of these databases. These are two of the main trade-offs. Relational databases give us the consistency without the availability. If we move over to something like a KV database or even a document database, Columnar especially, consistency drops down to 1 star, but we get 4 to 5 stars on availability. And this is just yet another manifestation of CAP theorem in action. And what we look at with that typically is not saying, oh, well, then you can't use Columnar because maybe the nature of our data fits in Cassandra, for example, or Druid really, really well. But the way we spin this kind of intersection or alignment is based on what risk we are incurring because of the nature of our data and the kind of database we're choosing. And if we're in cloud environments with highly distributed data, such as DynamoDB, our risk is with consistency. And that's going to be one of the main things we have to trade off and think about in this alignment.
It is teams, which seems at first blush like, well, how can you talk about the intersection of architecture and teams? So we have a lot of respect for the ideas behind team topologies and this idea of stream-enabled teams and enabling teams. And so what this approach to software development encourages you to do is to think about how would you objectively measure some impacts like this between architecture and something like teams. And so if you were trying to figure out, for example, so part of team topologies is this idea of you have a stream-enabled team and you have or a stream-optimized team and an enabling team that's giving them advice and assistance, et cetera. Now the question is, or a specialty team. Now the question is, are those teams slowing down your stream team? Because that's the goal, is to make that as fast as possible. So now if that's our goal, how can we measure that in a way that's consistent with architecture? Well, you can measure things like how many merge conflicts are coming in from the specialty team or the enabling team into the stream enable team, because the more merge conflicts that are coming in, the more they're imposing things and the more they're having to handle merge conflicts and the more it's slowing things down. So this is a measure of team impact for having something. Is the contribution they're making actually improving things, or are they creating so many complications that are actually instead slowing things down? Another way to think about this team intersection is how much effort does it take to implement a brand new feature? So one of the famous things that we talk about is the inverse Conway maneuver, where you really want domain-specific teams rather than separated by technical capabilities. But the question you have to ask yourself is, well, what if you're trying to build something like microservices, but you still have all your user interface people sitting in one place, or your developers somewhere else, or your data engineers somewhere else? You have to replicate that communication structure by Conway's law. And so how do you do that? You do it with JIRA tickets. And so measure the number of JIRA tickets it takes to implement a new feature. And if that's over 10, you've got communication issues in your organization. So it's a way of looking at the architecture, which is supposed to be domain focused, but our organization is not domain focused and is creating a bunch of artificial churn and friction that we can actually measure and try to address by observing that.
Well, and also if we look at the shape of various architectures, one of the aspects of that shape that does tend to influence team topologies the most is the overall modularity level of the particular architecture style. And the less modularity, architectural modularity we have in our architecture, the less effective enabling teams or complicated subsystem teams will actually be, because we're going to be getting in each other's way, as Neal just said. So that alignment is also kind of a key indicator of, do we have these great teams, and can we even leverage these kind of different team topologies due to the shape of our architecture?
Yep. So let's talk about another intersection, which is engineering practices. So one of the things you can use this approach to do is to, when you make messy trade-offs, can you mitigate the bad parts of the trade-off? So a common messy trade-off that you encounter in a lot of projects is a mono repo versus separate repo per service. So let's say that you choose a mono repo for good reasons, lots of trade-offs. What's the big danger that you have if you use a mono repo and you're trying to build some sort of distributed services? Well, the problem you run into is that it's very, very easy to create accidental coupling points between components in that system, because all the code base is there, the same code base, and it's easy. In fact, your IDE may just helpfully do that for you as part of an auto import, and you don't even realize you're reaching across an ecosystem to grab those things. And so one of the ways that, okay, we've decided to use a mono repo, now let's build an architectural fitness function in something like ArcUnit or NetArcTest or PyArcTest that says, make sure these components never get coupled to one another in any of my compilation targets. That's really the fear in the mono repo. And so once you translate what is the actual fear, the danger of using the mono repo, once you translate that into architectural terms, you can build architectural checks to make sure that you haven't accidentally done that, and now take advantage of the good parts of the mono repo and avoid some of the pitfalls that come along with it.
So I do have a question related to this, right? So, and this is probably controversial in that, on a team, should architects enforce engineering practices, or is that just solely the implementation team's domain?
I would say that goes back to the earlier answer to the question we had, which is it depends. And I think it depends on a lot of things, the size and sophistication of the team and the organization. Do you have a dedicated infrastructure team, or is that something that you're doing, or is it a shared responsibility and that sort of stuff? So, but I think that I don't see any good place where there's a strict isolation between those two roles. So there should be definitely feedback and collaboration, but I think it's organizational as to exactly how involved that is. Some of it has to do with how complicated the thing is they're building too. If you're building some sort of, very complicated space-based architecture, there's probably a lot more intersection between those parts.
And also, I think where that alignment comes in is also depends. It depends, but it also depends on the type of capabilities that we're looking for in the architecture. And let me give you an example of what I'm talking about. Let's say that our capability or architectural characteristic is extremely high levels of agility, the ability to respond quickly to change due to very aggressive time to market needs for this particular company. When a bug is identified, a new feature comes out, that change has to get to our end users as fast as possible. There are architecture styles that support high levels of agility. Microservices has 5 stars for agility. The n-tiered layered architecture has 1. And so when we look at the shape of that kind of architecture, the alignment now starts to play into the engineering practices as well. If we didn't need or experience, if we're not experiencing high levels of change, if we don't have a lot of maintenance, then these engineering practices become less significant than if we do incur high rates of change and we do have high need for agility. Because some of those engineering practices may impede maintainability, may impede testability, deployability, our deployment pipelines, and that's when this alignment starts to matter the most. So that's another one of those it depends moments.
That leads us to the next one, which is the intersection between architecture and business, right? So this tension, how do you navigate this tension between meeting short-term business goals and long-term architecture vision? Always a catch-22.
Sure. Oh, yes. And when we talk about a business environment, what we're talking about is, for example, is your business undergoing extreme cost-cutting measures because they're losing market share, they're losing money, or are they aggressively expanding into other markets? The type of architectures we have will influence that business's ability to do those things. Maybe it's undergoing high regulatory compliance as a necessity within your business or competitive advantage. The size of the business also impacts our architectures. Small business versus large businesses. Large businesses typically need more scalability, need the ability for evolutionary architecture or evolvability, adaptability. Whereas small businesses typically are more focused on the cost of that architecture from initially creating it to ongoing. The complexity of the business matters and things like constant change. But when we talk about the business environment, one of the other very important intersections that comes into play with business is with the domain as well. And as a matter of fact, Neal and I call this domain to architecture isomorphism. Isomorphism really meaning, does the shape of one thing match the shape of another? And when we talk about our business environment, does the shape of our problem domain match the shape of our architecture? And those of you listening are probably saying, Mark, what in the world are you talking about shape? What do you mean? Well, every architecture has a shape associated with it. For example, microservices is a prime example. The shape of that architecture is single purpose functions deployed as separate units of software with each owning its own data. That's the shape of that architecture style. Now, what about the shape of our domain? What in the world do you mean? Our domain has a shape. Of course it does. And that shape may involve things like time to market. The nature of data must be consistent. Maybe I've got highly semantically coupled data. Or maybe my business domain is highly semantically coupled functionality. What are the nature of my changes? Are we constantly replacing our presentation layer, our user interface, but all of our business stays the same, our data stays the same? That kind of change is technical in nature. That's that shape of that problem domain. And if we take the shape of an architecture like layered, where that's functionality is grouped by technical categories, that's a great alignment. Whereas if the nature of our changes are domain-based, we want a domain-shaped architecture in that case. So every business problem also has its own shape, the way of describing the needs and constraints within that business problem.
So I do have a question related to this, right? So I'd like to think of the business requirements as the problem domain and the architecture as the solution domain, right?
Sure.
Now, what do you do when these two do not match, the shapes of these two do not match? What are your options?
Well, there's really only two, Prem. That is, we could change the business domain or we can change our solution. And this is something that Neal and I both are working on a lot of material for, which is iterative architecture. Because the shape of our problem domain may match right now. But what happens in 4 years, 5 years? Suddenly, it's like putting a square peg in a round hole. So, Prem, this actually does happen. And it's up to the architect to always ensure this alignment of that shape. Generally, we will do architectural refactorings and iterate on that architecture as the shape of our problem domain continues to change. Where we run into trouble is when we don't pay attention to that alignment.
Yeah, inevitably business can change faster than architecture, and we're always playing catch up on trying to, and this is one of those alignments that we're constantly trying to achieve, and we're always half a step behind. But that's actually, I think, by its nature, we're always going to be a half step behind.
I don't know who coined this, but I think I saw this person on the Thoughtworks radar called inverse Conway maneuver. So yeah, I guess that's probably relevant in this context.
The Johnny Leroy coined that. He was considered the Department of Naming department when he was here. So he was good at coming up with names for things. So let's talk about one last intersection, which is I think it's required by law that you have to mention generative AI at least at some point during every podcast or public pronouncement by a company these days. And of course, there's a huge intersection between architecture and generative AI, but there are actually two kinds of intersections, and it's important to tease those things apart. The first of those intersections is the shiny one, which is, let's customize the LLM or, build RAG and build, and augment the output and all those sorts of things. And that's the very operational side of LLMs. And certainly there's a huge topic area, but that's really more of a specialization, almost more like analytical data or user experience or something like that. The general concern we have as architects and AI is operationalizing it. It's a shiny demo right now, but putting that shiny demo into production is tricky because now we need to get it to work at scale. And now we need to make sure that we have evals and guardrails and, the appropriate context and the correct filtering is going on. It's producing the right stuff and validating the output and all these things, reservability for LLMs. And so 38% of the blips on the radar had to do with generative AI, and almost none of them were LLMs. It was all ecosystem support for LLMs. And so that's, I think, the near-term huge intersection we're going to see. I mean, it's certainly useful for doing things like code generation, and Mark and I have actually had some great success of using the language part of LLMs to translate from pseudocode into platform-specific fitness functions. But that is actually the topic of the next installment of the podcast, because we got a lot of stuff to say about that and why that's an interesting approach. But that's another great use of Gen AI, because at the end of the day, large language models are language models, and they're really good at translating from one language into another one. And you can definitely leverage it to bootstrap yourself into some of these building some of the protections and defining some of the intersections we're talking about. So you can use it to go sort of meta and help you describe the other intersections that we identify as well. So what we've done today is used a whole lot of hand waving to describe each one of these intersections, but we're software architects at heart. We want a much more concrete way to express these intersections. And that's what the second part of this podcast is going to be, which is this idea of architecture as code. Take the intersections that we've talked about, but express them in code. Just like a building architect creates a plan that the builders follow, we can create plans for data intersections, implementation intersections, infrastructure, and we've got a lot of details about how to do that. That's what we're going to cover in the next episode, is how to make these descriptions of these intersections much more concrete.
And with that, we come to the end of this episode of the Thoughtworks Technology Podcast. Thank you very much, Neal and Mark. We look forward to the next episode, where we will talk about how architecture intent can actually be translated into working code.